Your eyes are far more than just windows to your soul. They are evolutionary masterpieces, each color carrying hidden advantages that helped shape human survival across thousands of years. What you see in the mirror every morning represents millions of years of adaptation, environmental pressure, and genetic refinement. Each shade tells a story of how your ancestors navigated different climates, lighting conditions, and survival challenges. From the protective power of deep melanin to the light-gathering efficiency of pale irises, every eye color emerged for specific reasons that still benefit you today. Most people think eye color is purely cosmetic, but science reveals a different truth. Your iris contains specialized structures that function like biological equipment, fine-tuned for particular environments and circumstances. The amount and distribution of melanin in your eyes determines not just appearance, but performance characteristics that can influence everything from visual acuity to disease resistance. Understanding these hidden advantages reveals why certain eye colors cluster in specific geographic regions and why some shades remain rare while others dominate global populations. The darkest eyes carry the strongest natural defenses. Deep brown and near-black irises contain dense concentrations of melanin, the same pigment that protects skin from harmful radiation. This biological armor absorbs ultraviolet light before it can penetrate deeper eye structures, reducing damage to the retina and lens. Early humans living in sun-drenched environments developed these darker shades as protection against constant exposure to intense daylight. The melanin acts like built-in sunglasses, filtering harmful wavelengths while maintaining clear vision. Beyond protection, dark eyes offer remarkable stability under varying conditions. Unlike lighter shades that shift and change with different illumination, brown and black irises maintain consistent appearance and performance. This stability translates to reduced eye strain and better visual endurance during prolonged exposure to bright conditions. The melanin also minimizes light scatter within the eye, creating sharper focus and reducing glare sensitivity. These advantages explain why over 70% of the global population still carries brown eyes, a testament to their evolutionary success. However, dark pigmentation comes with trade-offs. Dense melanin blocks not just harmful light, but also beneficial illumination needed for optimal vision in dim conditions. Brown-eyed individuals may struggle more in low-light situations compared to those with lighter irises. This limitation shaped migration patterns and settlement preferences throughout human history, with dark-eyed populations thriving in sun-rich regions while facing challenges in darker northern climates. At the opposite extreme, pale blue eyes represent a completely different evolutionary strategy. These irises contain minimal melanin, allowing maximum light penetration for enhanced vision in dim environments. The blue appearance results not from pigmentation, but from light scattering within the iris structure. Short blue wavelengths reflect outward, while longer wavelengths pass through, creating the characteristic color through the same physics that makes the sky appear blue. This light-gathering advantage proved crucial for populations settling in northern regions with limited sunlight and extended winter periods. Blue eyes enhance visual sensitivity in overcast conditions and twilight hours, providing survival benefits in environments where detecting movement or obstacles in low light could mean the difference between life and death. Archaeological evidence suggests this trait emerged relatively recently, around 6,000 to 10,000 years ago, through a single genetic mutation that rapidly spread through certain populations. The sensitivity that makes blue eyes advantageous in dark conditions becomes a liability under bright sun. Without melanin protection, these eyes face increased vulnerability to ultraviolet damage and intense glare. Blue-eyed individuals often experience greater light sensitivity and may develop certain eye conditions more readily than their darker-eyed counterparts. This explains why blue eyes remain concentrated in northern latitudes and occur less frequently in equatorial regions. Green eyes occupy a unique middle ground, balancing protection with sensitivity through moderate melanin levels combined with additional pigments. This intermediate position provides adaptability across varying light conditions without the extreme specialization of brown or blue eyes. Green irises can handle moderate sun exposure while retaining enough sensitivity for decent low-light performance. This versatility may have offered advantages in temperate regions with seasonal lighting changes and mixed environments. The rarity of green eyes, found in only about 2% of the population, reflects the precise genetic conditions required for their formation. Too much melanin shifts them toward brown, while too little moves them toward blue. This narrow window creates an unstable but visually striking color that responds dynamically to lighting changes. Green eyes often appear to shift between moss, gold, and emerald tones depending on surroundings and illumination, a characteristic that has inspired countless cultural associations and folklore throughout history. Hazel eyes demonstrate another form of adaptive versatility, containing intermediate melanin levels that allow them to function effectively across diverse lighting conditions. Their ability to shift between green, gold, and brown tones reflects real changes in how light interacts with varying pigment distributions within the iris. This dynamic quality provides moderate protection in bright conditions while maintaining reasonable sensitivity in dimmer environments. The genetic complexity behind hazel eyes suggests they represent blended inheritance patterns rather than simple dominant or recessive traits. This mixing creates individuals who can adapt visually to changing conditions throughout the day or across seasons. Hazel-eyed people often report that their eye color appears to change with clothing, mood, or lighting, a phenomenon based on how surrounding colors and illumination interact with their iris pigmentation. Amber eyes showcase an entirely different evolutionary pathway, characterized by high levels of specialized pigments that create a distinctive golden appearance. Unlike hazel eyes that shift with conditions, amber irises maintain their honey-colored hue under all lighting circumstances. This stability, combined with their striking appearance, may have provided social rather than purely visual advantages. The golden coloration resembles eye colors found in many predatory animals, potentially conveying subliminal signals of alertness or intensity. The extreme rarity of true amber eyes, present in less than 5% of the population, adds to their distinctive impact. Often confused with light brown or hazel, genuine amber eyes display uniform golden tones without the variability characteristic of other colors. This consistency may reflect highly specific genetic combinations that produce stable pigment distributions, optimized for particular environmental or social functions. Grey eyes represent perhaps the most unusual adaptation, containing even less melanin than blue eyes but scattering light across broader wavelengths. This creates a neutral, steel-like appearance that remains stable under various lighting conditions. The extreme light sensitivity of grey eyes may have provided advantages in consistently overcast northern climates where maximizing available illumination was crucial for survival. The rarity and distinctive appearance of grey eyes, found in less than 3% of the population, creates a unique visual signature. Unlike the warm tones of brown or the vivid hues of green and blue, grey eyes project coolness and neutrality. This emotional ambiguity may have offered subtle social advantages in situations requiring perceived objectivity or emotional control. These variations in eye color represent just the beginning of understanding how human vision adapted to diverse environments and challenges. Each shade carries specific advantages and limitations that influence survival, reproduction, and cultural development throughout human history. Beyond the primary eye colors, human vision reveals even more specialized adaptations that shaped survival across different environments and challenges. The most extreme example appears in individuals with heterochromia, where each eye displays a different color or where variations occur within a single iris. While this condition affects less than 1% of the population, it demonstrates how genetic flexibility can create unique visual advantages that extend beyond simple pigmentation patterns. Heterochromia emerges when melanin distribution becomes asymmetrical during early development, often due to localized genetic variations or developmental disruptions. Rather than representing a defect, this asymmetry may signal underlying genetic diversity that provides adaptive advantages in unexpected ways. Some researchers suggest that the genetic mechanisms responsible for heterochromia might also influence other physiological traits, creating individuals with enhanced adaptability to environmental changes or stress responses. The visual impact of heterochromia extends beyond mere appearance. Having eyes with different light-gathering capabilities might provide subtle advantages in situations requiring rapid adaptation to changing illumination. One eye optimized for bright conditions paired with another better suited for dim lighting could theoretically offer enhanced visual flexibility, though scientific evidence for this remains limited. What is clear is that heterochromia demonstrates the remarkable plasticity of human genetic expression and development. Cultural responses to heterochromia throughout history reveal how unusual physical traits can influence social dynamics and survival strategies. Many societies viewed individuals with different colored eyes as possessing special abilities or supernatural connections, potentially providing social advantages that compensated for any visual limitations. This cultural dimension adds another layer to understanding how eye color variations influenced human evolution and social development. The distribution of eye colors across global populations tells a story of human migration, adaptation, and genetic mixing that spans tens of thousands of years. Northern European populations show the highest frequencies of light-colored eyes, reflecting adaptations to low-light environments and reduced solar radiation. These regions experience extended winter periods with limited daylight, creating selective pressures that favored enhanced light sensitivity over UV protection. Conversely, equatorial populations maintain dark eye predominantly colors, with brown and near-black irises providing essential protection against constant high-intensity sunlight and UV exposure. THED elevate persistence of these darker shades in sun-rich environments demonstrates their continued survival value even in modern contexts, where sunglasses and other protective technologies are available. Intermediate regions show more mixed distributions, with populations carrying various combinations of eye colors that reflect both local adaptations and historical migration patterns. The Mediterranean basin, for example, displays a blend of brown, hazel, and green eyes that may represent optimal adaptations to the variable lighting conditions and seasonal changes characteristic of temperate climates. Modern genetic research has revealed that eye color inheritance involves far more complexity than the simple dominant and recessive patterns once taught in basic biology classes. Multiple genes interact to determine final iris pigmentation, with some variants having subtle effects that only become apparent under specific environmental conditions. This polygenic inheritance explains why eye color can sometimes appear to skip generations, or why children may have colors that seem unrelated to their parents. The OCA2 and HERC2 genes play primary roles in melanin production and distribution, but at least 15 other genetic loci contribute to final eye color determination. Some of these genes also influence hair and skin pigmentation, creating the coordinated appearance patterns seen in many populations. Others affect iris structure and light scattering properties independently of pigmentation, adding another dimension to the genetic architecture underlying eye color variation. Recent studies have identified rare genetic variants that produce unusual eye colors or patterns not easily categorized within traditional classifications. Some individuals carry mutations that create sectoral heterochromia, where portions of a single iris display different colors in distinct patterns. Others have genetic combinations that produce eye colors that shift dramatically with age, starting light in childhood and darkening significantly by adulthood. The interaction between genetics and environment continues to influence eye color expression throughout life. UV exposure can gradually darken light-colored eyes over decades, while certain medications and medical conditions can alter iris pigmentation in unexpected ways. These dynamic changes demonstrate that eye color represents an ongoing biological process, rather than a fixed trait determined solely at birth. Understanding these genetic mechanisms has practical implications beyond satisfying scientific curiosity. Eye color can influence responses to certain medications, particularly those affecting vision or light sensitivity. Individuals with light-colored eyes may require different dosages of drugs that cause pupil dilation, while those with dark eyes might need adjusted treatments for conditions involving light therapy. The relationship between eye color and various health conditions continues to emerge through large-scale population studies. Light-colored eyes show associations with increased risks of certain eye diseases, but decreased susceptibility to others. Dark eyes demonstrate different patterns of age-related changes and responses to environmental stresses. These correlations help medical professionals provide more personalized care based on genetic risk factors. Beyond health implications, eye color variations influence daily life in subtle but meaningful ways. Individuals with light-sensitive eyes naturally develop behavioral adaptations like seeking shade, wearing protective eyewear, or organizing activities around lighting conditions. Those with dark, stable eye colors may gravitate toward environments and activities that take advantage of their enhanced glare resistance and consistent visual performance. The psychological and social dimensions of eye color add yet another layer to their evolutionary significance. Research suggests that people unconsciously associate different eye colors with specific personality traits or capabilities, potentially influencing social interactions and opportunities across cultures, but often reflect These associations vary functional advantages historically linked to different iris pigmentations. Eye color preferences in mate selection may represent vestigial recognition of adaptive advantages, with individuals subconsciously attracted to traits that complement their own visual capabilities or provide genetic diversity for offspring. This process could help maintain eye color variation within populations while ensuring optimal visual adaptations across different environmental niches. The study of eye color evolution continues to reveal new insights about human adaptation, migration, and genetic diversity. As genetic sequencing becomes more sophisticated and population databases expand, researchers uncover previously unknown variants and inheritance patterns that add complexity to our understanding of this fundamental human trait. Modern genetic analysis has uncovered unexpected connections between eye color and broader physiological systems that extend far beyond vision alone. The same genetic pathways that control melanin distribution in the iris also influence melanin production throughout the body, creating coordinated patterns that affect skin tone, hair color, and even internal organ pigmentation. These linked systems suggest that eye color variations represent visible markers of more comprehensive genetic adaptations that shaped human survival across diverse environments. The TYRP1 and TYR genes, which control melanin synthesis, demonstrate how eye color connects to systemic biological functions. Variations in these genes affect not just iris pigmentation, but also influence melanin production in the inner ear, potentially impacting hearing sensitivity and balance. Some research indicates that individuals with lighter eye colors may experience different auditory processing characteristics compared to those with darker eye colors, darker eyes, though the practical implications remain under investigation. Melanin distribution patterns also correlate with immune system variations that may have provided selective advantages in different geographic regions. The same genetic mechanisms that produce dark eyes often coordinate with enhanced production of certain immune factors, potentially explaining why populations with predominantly brown eyes show different disease susceptibility patterns compared to light-eyed groups. These correlations highlight how eye color serves as an external indicator of deeper biological adaptations. The relationship between iris pigmentation and circadian rhythm regulation represents another unexpected connection. Melanin in the eye influences how light signals reach the brain structures responsible for sleep-wake cycles and seasonal mood regulation. Individuals with lighter eyes may experience more pronounced responses to seasonal light changes, potentially making them more susceptible to conditions like seasonal affective disorder, but also more sensitive to beneficial light therapy treatments. Recent neurological research has identified variations in brain structure and function that correlate with eye color, though the mechanisms behind these associations remain unclear. Some studies suggest that the genetic factors influencing iris pigmentation also affect neural development in regions responsible for visual processing and attention. Light-eyed individuals may show different patterns of brain activation during visual tasks compared to dark-eyed participants, potentially reflecting deeper evolutionary adaptations to different lighting environments. These neural variations extend to pain perception and sensitivity, with some research indicating that eye color may influence responses to certain types of discomfort or stress. The genetic pathways that control melanin production appear to interact with neurotransmitter systems involved in pain processing, creating subtle but measurable differences in how individuals with different eye colors experience and respond to various stimuli. The evolutionary timeline of eye color development reveals how rapidly human populations adapted to new environments following major migrations. Genetic evidence suggests that the mutations responsible for light eye colors spread through certain populations within just a few thousand years, an extremely rapid pace for evolutionary change. This speed indicates powerful selective pressures that favored these traits in specific environmental contexts. Archaeological and genetic evidence points to multiple independent origins for light eye colors, with different populations developing similar adaptations through distinct genetic pathways. European populations primarily developed light eyes through variations in the OCA2 and HERC2 genes, while some Asian groups achieved similar results through different genetic mechanisms. This convergent evolution demonstrates how environmental pressures consistently favored enhanced light sensitivity in regions with reduced solar illumination. The geographic distribution of eye colors also reveals how ancient trade routes and cultural exchanges influenced genetic mixing patterns. Populations along major trading pathways show more diverse eye color distributions compared to isolated groups, reflecting centuries of genetic exchange that created unique combinations of adaptive traits. These patterns help researchers trace human migration and cultural interaction histories through biological markers. Climate change events throughout human history appear to have influenced eye color evolution in measurable ways. Ice Age periods that reduced available sunlight may have accelerated the spread of light-colored eyes in affected regions, while subsequent warming periods created selective pressures that favored intermediate pigmentation levels. These cyclical environmental changes help explain the complex geographic patterns of eye color distributions seen today. The molecular mechanisms underlying eye color expression continue to reveal new levels of complexity as research techniques improve. Recent discoveries show that iris pigmentation involves not just melanin quantity, but also the size, shape, and distribution of melanin-containing structures within the eye. These microscopic variations create subtle differences in light interaction that can influence visual performance even among individuals with apparently similar eye colors. Epigenetic factors that influence gene expression without changing DNA sequences add another layer to eye color determination. Environmental influences during fetal development, maternal nutrition, and even stress levels (PIG) can affect how mentation genes are expressed, creating variations in final eye color that cannot be predicted from genetic analysis alone. These discoveries highlight the dynamic nature of trait development and the ongoing interaction between genetics and environment. The study of eye color in mixed populations has revealed unexpected inheritance patterns that challenge traditional genetic models. Some children display eye colors that appear impossible based on their parents' genetics, leading researchers to discover previously unknown genetic variants and interaction patterns. These rare cases provide valuable insights into the full complexity of human pigmentation genetics. Advanced imaging techniques now allow researchers to analyze iris structure at the cellular level, revealing microscopic patterns unique to each individual. These iris patterns remain stable throughout life and provide more reliable identification than fingerprints, leading to their use in biometric security systems. The same structural variations that create these unique patterns also influence how light interacts with the eye, affecting visual performance in subtle but measurable ways. The relationship between eye color and visual acuity extends beyond simple light sensitivity to include factors like contrast detection, color discrimination, and depth perception. Individuals with different iris pigmentation levels show varying performance on standardized vision tests, even when overall visual acuity appears similar. These differences may reflect evolutionary adaptations to specific visual challenges encountered in different environments. Photoreceptor distribution patterns in the retina also correlate with iris pigmentation, suggesting coordinated development of the entire visual system. Light-eyed individuals may have different ratios of rod-to-cone cells, potentially affecting night vision capabilities and color perception. These variations demonstrate how eye color represents just one visible aspect of comprehensive visual system adaptations. The protective mechanisms associated with dark eye colors extend beyond simple UV absorption to include enhanced resistance to certain types of light-induced damage. Dense melanin concentrations can neutralize harmful free radicals generated by light exposure, providing ongoing cellular protection that accumulates over decades. This protective effect may contribute to lower rates of certain age-related eye conditions in dark-eyed populations. Conversely, the enhanced light sensitivity of pale eyes may provide advantages in detecting subtle environmental changes or movement patterns that darker eyes might miss. This heightened visual sensitivity could have offered survival benefits in environments where early detection of predators, prey, or environmental hazards provided crucial advantages. Modern applications of this enhanced sensitivity appear in fields requiring exceptional visual discrimination abilities. The interaction between eye color and artificial lighting represents a modern challenge that human vision systems never evolved to handle. Different iris pigmentation levels respond differently to LED lights, fluorescent fixtures, and computer screens, potentially creating varying levels of eye strain and fatigue. Understanding these interactions helps optimize lighting design for diverse populations and may influence recommendations for protective eyewear. Cultural evolution has also shaped how eye color variations are perceived and valued across different societies. Some cultures developed preferences for specific eye colors that may have influenced mate selection patterns over generations, potentially affecting the genetic distribution of these traits. These cultural factors add a social dimension to the biological evolution of eye color that continues to influence human genetic patterns today. The future of eye color research promises even more detailed understanding of how these traits influence human biology and behavior. Advanced genetic analysis techniques continue to identify new variants and interaction patterns, while improved imaging methods reveal previously hidden aspects of iris structure and function. These discoveries will likely uncover additional connections between eye color and broader physiological systems that remain unknown today. Don't just watch the world. Subscribe and understand. The medical implications of eye color variations continue expanding as research reveals connections between iris pigmentation and drug metabolism patterns. Individuals with different melanin concentrations process certain medications at varying rates, particularly those affecting vision or neurological function. Light-eyed patients may require adjusted dosages for drugs that cause pupil dilation during eye examinations, while darker-eyed individuals might need different approaches for treatments involving light-based therapies. Anesthesia responses also correlate with eye color through mechanisms still being investigated. Some studies indicate that redheads with light eyes require higher doses of certain anesthetic agents, while individuals with dark brown or black eyes may show enhanced sensitivity to pain medications. These variations likely reflect the shared genetic pathways that control both pigmentation and neurotransmitter processing throughout the body. The relationship between iris coloration and vitamin D metabolism presents another fascinating connection. Light-eyed individuals living in sun-limited regions may synthesize vitamin D more efficiently from available UV exposure, while those with dark eyes might require dietary supplementation to maintain optimal levels. This metabolic difference could influence bone health, immune function, and seasonal mood regulation across different populations. Blood vessel patterns within the iris also vary by pigmentation level, affecting circulation and potentially influencing eye pressure regulation. Dense melanin deposits can alter how blood flows through the delicate capillary networks that nourish iris tissues, creating subtle differences in how various eye colors respond to medications that affect ocular pressure or circulation. Temperature regulation around the eye socket shows measurable differences based on iris pigmentation. Dark eyes absorb more radiant heat, potentially warming the surrounding tissues and affecting tear production patterns. Light eyes reflect more thermal energy, possibly contributing to cooler orbital temperatures that influence blink rates and moisture retention. These thermal variations may have provided adaptive advantages in different climatic conditions throughout human evolution. The optical properties of different eye colors extend beyond simple light transmission to include complex interactions with polarized light and glare patterns. Brown and black eyes filter polarized reflections more effectively than lighter colors, reducing visual disturbance from water surfaces, snow, or glass. This natural polarization filtering may have offered hunting and navigation advantages for populations living near reflective environments. Blue and grey eyes demonstrate different polarization responses that could enhance detection of atmospheric phenomena or distant objects under specific conditions. The light scattering properties that create their color also interact with polarized skylight in ways that might improve visual contrast during certain weather patterns or times of day. Accommodation speed, the ability to rapidly focus on objects at different distances, varies subtly among eye colors through mechanisms involving iris muscle coordination and lens flexibility. These differences remain within normal ranges but may influence visual fatigue patterns and optimal working distances for detailed tasks. Dark-eyed individuals might show slightly different accommodation responses compared to light-eyed counterparts. The pupil response patterns associated with different iris colors reveal another layer of visual adaptation. Dense pigmentation affects how quickly pupils can dilate or constrict in response to light changes, potentially influencing adaptation speed when moving between bright and dim environments. This responsiveness could have provided survival advantages during activities requiring rapid visual adjustment. Night vision capabilities extend beyond simple light sensitivity to include adaptation speed and low light acuity patterns. While light eyes gather more available illumination, the trade-off in contrast sensitivity might affect performance under specific nocturnal conditions. Dark eyes may lose some light-gathering ability, but maintain better definition between subtle shade variations in dim conditions. Color discrimination abilities also correlate with iris pigmentation through complex interactions between filtering effects and retinal processing. Different eye colors may show enhanced sensitivity to particular wavelength ranges while experiencing reduced discrimination in others. These variations could influence artistic abilities, occupational preferences, or navigation strategies that rely on color-based environmental cues. The aging process affects eye colors differently based on their initial pigmentation patterns. Light eyes may darken gradually over decades as melanin production increases with cumulative sun exposure, while dark eyes typically remain stable or show only minimal changes. These aging patterns reflect ongoing biological responses to environmental factors throughout life. Hormonal influences on eye color expression create dynamic changes that extend beyond childhood development. Pregnancy, puberty, and certain medical conditions can alter iris pigmentation temporarily or permanently through mechanisms involving melanin synthesis regulation. These changes demonstrate the continued plasticity of eye color expression throughout the human lifespan. Seasonal variations in eye color appearance reflect both physiological changes and optical effects from varying light exposure patterns. Some individuals report subtle shifts in their iris coloration between summer and winter months, possibly reflecting melanin production changes or structural modifications in response to different illumination levels. The protective mechanisms of dark eye colors include resistance to specific wavelengths that can cause cumulative damage over time. Beyond UV protection, dense melanin absorbs high-energy blue light that increasingly dominates modern artificial lighting environments. This natural filtering may provide advantages in screen-heavy occupations or digital device usage patterns. Inflammatory responses within the eye show different patterns based on iris pigmentation levels. Dark eyes may demonstrate enhanced resistance to certain types of irritation, while showing different healing responses to injuries or infections. These variations could influence treatment strategies and recovery expectations for various eye conditions. The genetic stability of eye color traits varies significantly among different populations and inheritance patterns. Some eye color variants show high stability across generations, while others demonstrate more dynamic expression that can change based on environmental factors or genetic recombination patterns. Understanding these stability differences helps predict inheritance likelihood and identify populations at risk for certain eye-related conditions. Developmental timing for final eye color expression differs among various pigmentation patterns. While most eye colors stabilize during early childhood, some variants continue evolving into adulthood or show sensitivity to environmental factors throughout life. These developmental patterns reflect the complex genetic and environmental interactions that shape final iris appearance. The molecular structure of melanin itself varies between different eye colors, creating distinct chemical properties that affect light interaction and biological function. Eumelanin and pheomelanin ratios differ among brown, hazel, and amber eyes, potentially influencing protection levels and visual performance characteristics specific to each variant. Cellular organization within the iris demonstrates unique patterns for each eye color that extend beyond simple pigment concentration. The arrangement and density of melanin-containing cells create microscopic structures that interact with light in complex ways, contributing to the distinctive appearance and functional properties of each iris type. Research into artificial eye color modification reveals how deeply integrated these traits are with overall eye health and function. Colored contact lenses and surgical procedures that alter iris appearance can affect natural protective mechanisms and visual performance in ways that highlight the sophisticated biological engineering behind natural eye color variations. The evolutionary future of eye color traits faces new selective pressures from modern environments dominated by artificial lighting and digital displays. These novel environmental factors may influence which eye color variants provide advantages in contemporary settings, potentially affecting long-term genetic trends in human populations. Advanced genetic therapies now being developed could potentially modify eye color expression, raising questions about the broader biological consequences of altering these deeply integrated traits. Understanding the full scope of eye color functions becomes crucial as medical technology approaches the ability to manipulate these characteristics. The intersection of eye color research with personalized medicine continues expanding as genetic analysis becomes more sophisticated and accessible. Individual genetic profiles that include eye color variants may soon inform customized treatment approaches for vision-related conditions, drug therapies, and preventive care strategies. Population genetics studies using eye color markers help trace human migration patterns and genetic diversity with increasing precision. These biological signatures provide insights into historical population movements and mixing events that shaped current global genetic distributions. The complexity of eye color inheritance challenges traditional genetic counseling approaches and requires more nuanced understanding of polygenic traits and environmental interactions. Modern genetic counseling increasingly incorporates these complex inheritance patterns to provide accurate information about trait transmission likelihood. Environmental health research increasingly recognizes eye color as a factor in assessing individual risk for light-related injuries and occupational hazards. Understanding these variations helps develop more effective protective equipment and safety protocols for different populations. The study of eye color continues revealing unexpected connections that demonstrate how seemingly simple traits reflect sophisticated biological adaptations shaped by millions of years of evolutionary pressure and environmental interaction. Your eye color represents far more than aesthetic appeal. It embodies millions of years of human adaptation, environmental pressure, and genetic refinement that continues shaping your daily experience. From the UV-blocking power of deep brown eyes to the light-gathering efficiency of pale blue irises, each shade carries functional advantages that helped your ancestors survive and thrive. These traits influence everything from medication responses to visual performance, connecting your iris pigmentation to broader biological systems throughout your body. Understanding these hidden advantages reveals why certain colors cluster in specific regions and how ancient environmental pressures still benefit you today. Don't just watch the world, subscribe and understand.